There are two types of electrochemical cells, voltaic cells, which we covered in our last video, and electrolytic cells, which we're going to cover in this video. So electrolytic and electrochemical cells are different names. They mean different things. Electrochemical being, I have two types, and electrolytic being today's lesson. So don't get those mixed up. And when we were talking about voltaic cells, I started by a magic show happening. And in that magic show, it spontaneously happens. And Volta wants to be a part of that. He sticks those electrodes in his ears to be a part of that, right? And so with an electrolytic cell, though, there's no magic show. You see, it's a non-spontaneous reaction. I put it all together, and it sits there on the table, and it does nothing. There's no magic. So the first thing I want to talk about is the fact that it's a non-spontaneous reaction. So the first example in your notebook is this one, where I have a solution of copper sulfate. Now, in my solution of copper sulfate, we all know that that beaker of copper sulfate is going to sit there on the lab bench and not do anything. That's because here are my species lists. I have this, this, and this, and this. And if I put my finger and try to find my strongest oxidizing agent, it'll be this one, and my strongest reducing agent will be this one. And when I look it up in my data booklet, copper 2+ and water for my reducing agent are like this. That waterfall is going way uphill. It is really, really, really non-spontaneous. Nothing's going to happen. Non-spontaneous. Just sits there. Okay? But there is a way to force the reaction to happen. There is a way to force that copper to pick up those two electrons and become copper solid. And the way we're going to force it, just like we would force water up a waterfall, is we need a pump. We need something that physically pushes those electrons against what they would naturally want to do, against their natural potential. And so we need to add a power source to our list here. Now, a power source can be a battery. Well, actually, it's always a battery pack of some kind, right? Maybe I plug it into the wall. Maybe I plug it into a battery pack, or maybe I have like a D-cell battery that I hook it up to. But in either case, I have to put a power to it, put a battery pack to it. And that power source is going to convert our electrical power into chemical reactions. Okay, so I'm taking electrical power and doing chemical reactions. It's the exact opposite of the voltaic cell. The voltaic cell took chemicals and made electricity. This, I'm going to take electricity and I'm going to make the chemicals do things. Now, we're still going to have electrodes. We're still going to have electrolytes. I still have a cathode and an anode, and my electrons are going to move from the anode to the cathode in the wire. This is the same list as the voltaic cell. The cathode was called a positive, and it was the site of reduction, and the anode is negative, and it was the site of oxidation. Here's a big change. The cathode is going to be our negative post so that the cations are attracted to it, and so that the electrons can be picked up from there, because I'm going to have electrons, it's the negative, and the anode is going to be positively changed. Other than that, though, this list of figuring out what goes where and what things are called and what direction do things move, the list is the same. Just that little tiny difference, and then a power source, and then electricity is making our chemicals do things. Okay, so let's go over here and let's take our example, which is this copper solution. And in example 1 in your notebooks, it talks about how I have a copper solution and I'm going to stick some electrodes in it. And the electrodes I'm going to choose are some carbon. I want to choose something inert, okay, because something non-reactive. If I choose carbon graphite, or I could choose platinum or palladium, anything that I know is going to be non-reactive and is not going to interfere in my species list. So I'm going to pick carbon graphite for my electrodes. Okay, can you see that? Yep. Okay, so I'm going to pick that for my carbon graphite electrodes. And I'm going to stick those electrodes in the solution, and I'm going to hook up a power source to it. So here's my battery pack. Okay, and remember the battery packs, the big ones you get in the science lab, and there's always like a red and a black, and I have to stick my alligator clips into those, and then off they go to the experiment. So on those, the red and the black posts that you plug it into, one of those will be labeled as positive and the other will be labeled as negative, right? The red is the positive and the black is the negative. Now, because this says positive on the power pack at this end, and because I plugged the power pack onto this stick, that makes this electrode be, well, the positive electrode is the anode. So that makes this stick be the anode because I plugged it into the positive end of the battery, which means if I plug the battery in the other way, this would then be the cathode, right? If I flip the battery around. So I've got to look at the symbols on the battery in order to determine that this is the anode because it's positively charged. This is the cathode because it is negatively charged. And I didn't finish labeling this, so I'm just going to put carbon graphite there too. So in this example, the cathode is my this carbon graphite, and my anode is that carbon graphite. Okay. So now I'm also asked in this question to like say the rest of the stuff, where are the electrons going and where, et cetera, et cetera. So let's talk about the electrons. The electrons still move from the anode to the cathode in the wire. So the electrons are still going to come out of the battery this direction and fulfill this is a big negative charge, and they're going to come out of this end of the electrode and go back to the battery this direction there. Okay, so there's my electrons from the anode to the cathode. My cations are going to travel to the cathode within this solution. So the only cations I have is my copper 2+. So my copper 2+, which is going to be in my solution here, and it's going to go towards the cathode, so it's going to be attracted there. And when it gets there, because it's the strongest oxidizing agent, my copper 2+ is going to gain 2 electrons and become copper, just like I said I wanted it to. I just said I wanted to force it to happen. So it's cramming these electrons. The electrons are flying out of this battery, and it's cramming them all into this stick. This stick is so super negative that these positively charged cations are like, oh, yes, please. And it grabs those 2 electrons and becomes copper. Meanwhile, the SO4 2-, which are our anions, are attracted to the anode. Now that SO4 2- hangs there waiting. It's like anticipating its turn, but for now, it's not my strongest reducing agent. The water is. So the water that's also in this situation, that's also beside the anode, becomes my reducing agent. So my water reaction, which looks like this, 2 waters are going to form 4 electrons and 4 H+ and an O2 gas. Is that right? Yeah. And so that's that reaction there, 4 electrons and 4 H+ and an O2 gas. So I'm writing that down. So this is my strongest oxidizing agent. This is my strongest oxidizing agent. It is my gain of electrons reduction reaction, which is happening at the cathode. This is my strongest reducing agent. It is my loss of electrons, my oxidation reaction that's happening at the anode. And then my net reaction would be, well, same as last time. I need to balance my electrons and then write my net. And that would be my net redox reaction that's happening in this situation as I am forcing this non-spontaneous reaction to happen. Okay, one more example and we'll talk about observations at the same time. Okay, so this is example 2. It says that an electrocurrent is passed through a solution of nickel 2 nitrate using inert electrodes. Predict the anode and cathode reactions, overall reaction, and draw a diagram of this electrolytic cell. Okay, so here's the diagram of the electrolytic cell. An electrocurrent is passed through 2 inert electrodes. I chose to have PT as my inert electrode, but you could choose carbon graphite or PD. In fact, you know what? I can choose anything that wouldn't interfere here. So whatever, right? Like gold would work too because it's so high up on my oxidizing agents that it wouldn't play a part. Okay, so here is my solution of nickel nitrate. Here's my species list. So that's the beginning of the diagram. And then I have that my Here's my species list. I have nickel, I have nitrate, I have water, I have platinum. I need to put my finger and find my strongest oxidizing agent. That's what this will be. I put my finger and I find my strongest reducing agent, and I hit water first on my reducing agents. If that was too fast, you might need to go back and watch the video on predicting redox reactions in order to know what I mean about finding these strongest ones. So once I find it, I write my net. So this is the nickel that's going to react and the water that's going to react. You can see it's a non-spontaneous waterfall. This is my gain of electrons reduction. This reaction is happening at the cathode, and this is my loss of electrons oxidation happening at the anode. So here's my net reaction. Now, in order to draw a fully labeled diagram, I have to go back here and I have to add that because this is a negative post here, that this is going to be my cathode. And because this is a positive post, this is going to be my anode. And the electrons go from the anode to the cathode. So the electrons are going to be going this way from the anode to the cathode. Now, I arbitrarily chose to draw my battery with the negative on the right and the positive on the left. You could draw your battery the other direction, and you just would have the electrons flowing the other way, and you would be 100% correct. It would just be that everything is the exact opposite in your diagram. Okay, so because I have made that negative on my battery, the negative end of my battery, then that's the cathode stick. And so what's attracted to the cathode? The cations. And what's attracted to the anode? The anions. But also the water is also attracted there because the water is the one that is my oxidation half reaction. So the water is going to be going in that direction as well. So that's a fully labeled, that's included all of these things in my diagram. Now let me just talk about observations, because that's something else you're going to be asked. What would we observe happening at the cathode, and what would we observe happening at the anode? So here are my answers, but in order to come up with that, I had to do a little bit of thinking for that. So what ends up being my answers are this. So if this is the cathode reaction, this is what is forming at the cathode. So let's just look here. So my nickel 2 pluses are coming along. Those electrons have been fired out of the battery. Here they come, here they come, here they come. Right, they get there. The Na2 plus picks them up and becomes nickel solid. And that nickel solid builds up here along that stick. And so what I'm going to see along the cathode is I'm going to see a gray solid forming. That's my nickel that I end up forming. And the mass will increase because I'm, adding to that stick. And so those are observations. Like, have I got this working? Am I proving this theory? I can lift it up and I can weigh it, or I could see that I formed some sort of gray solid metallic looking substance on the outside. So what would we see at the anode? Well, at the anode reaction, I need to change my color of pen here. I'll go with black, I guess. My anode reaction, I'm forming these two species. So the water is going to go over here. The water is going to give up its electrons, 4 of them, 3, 4, and it's going to become oxygen, and it's going to become H pluses. So I'm going to see bubbles of oxygen, that this water that goes over here and drops off its electrons, the water becomes some oxygen. I'm going to see some bubbles. So I can't say that I see oxygen because I'm not that good. I don't know if it's oxygen or hydrogen or carbon dioxide. I just can see bubbles. So you have to be really careful. Your observations have to be things that you can see or hear, or they are not inferences. Inferences are things that that's an eyeball, by the way. Inferences are things that you have figured out. So all I see are bubbles. So that's what I write down as my observation. And those bubbles will relight a glowing splint. Remember, like an elephant toothpaste experiment where I blew out the thing and I put it back in the bubble and it relit, right? Relighting a glowing splint means that I have oxygen. So these are my observations. I infer then that it was oxygen and not carbon dioxide. I'll also be forming my H+. The H+ will be seen as a pH decrease, maybe by a pH meter, or maybe because blue litmus paper will all of a sudden turn red. So those are my observations for this electrolytic cell. And that's the electrochemical cells. The second type of electrochemical cells, electrolytic cells, non-spontaneous cells.